And as always, a small announcement. This will be recording, as Aaron said, and feel free to close your cameras, or if it's open, just be sure about that. So, Aaron, if you want, we can start. And also, Jess is okay with that.
Perfect. So I'll get started here. So today we're going to be chatting about a new kind of chat protocol suite, which we're going to be calling Logos Chat. And today's kind of focus is going to be on the encryption and kind of privacy implications of that. Consider this maybe the first of many talks about this protocol suite, and we're kind of looking at a subsection today just to kind of break it down into parts to make it a little bit easier to process. So maybe not all the answers will get answered today, but some portion, and through a series of these talks we can get kind of everything covered. And so I think the first question we have to talk about is, what is Logos Chat? And the definition I'm using is, a suite of protocols that enable private human-to-human communication. There's an emphasis on a suite of protocols. This isn't just one big monolith. It's a collection of well-thought-out components that we can, use modularly. Private, to refocus on our commitment to privacy. And then also the human-to-human component, emphasizes that the use case we're working on here is the chat one, not necessarily message passing, which sometimes can be confused for messaging. So this is human to human, not machines or anything else in that kind of capacity. And so we go, what are we going to talk about today? We're going to kind of focus on how's this protocol suite structured, kind of some high level discussion, just because we need to have that out of the way. And then we're going to dive into how does the encryption work at the various levels. And namely, what is the metadata leakage that this leads to. Things we're not going to talk about today is how messages are routed, interoperable content management, as well as identity, because those are further work pieces. And so we're going to try to keep it a little bit focused, and hopefully we can squeeze it into time. How we're going to go about that today is we're going to talk about the motivations on why do we need another one, kind of get that out of the way. Talk about this conversations abstraction, go over a high-level flow about how does messages work and how do these different protocol components fit together. We'll dive back into one-on-one chat operation and kind of get into some details around the encryption and the privacy there, as well as talking about compatibility concerns in a peer-to-peer network. And then if there's time, we can highlight some of the items that haven't been talked about yet. Diving into that motivation section, the question is why do we want to build yet another chat platform? I've gone through and reviewed all of them. There is a post on the VAC forum, which we'll have a link to on the next slide, that kind of highlights where all the other chat protocols are and whether or not they suit our needs. And what we found is we have this unique kind of spot between focusing on participant privacy as well as being peer-to-peer optimized. A lot of solutions out there have the privacy but rely on centralized infrastructure or sacrifice privacy in terms of usability to some capacity. And so the existing solutions don't quite fit in our case, because we're looking for this small sliver of can be run in the peer-to-peer context, so censorship resistant, as well as having the high privacy to make sure that people are protected while using it, and try to find a way that makes that scale. So we're kind of in this unique kind of space here in this Venn diagram. If we start talking about privacy, we should kind of loosely define what privacy we care about. There needs to be no linkage of social graph, so social graph secrecy. It should be impossible for people to tell who is communicating completely. We need to make sure that conversations don't leak metadata around which messages belong to them, so activity, which messages are being sent, who's a part of that conversation, how often are people communicating in that conversation, does that conversation exist? We also need sender anonymity to make sure that payloads aren't linked back to senders to a degree. as well as user activity anonymity. The protocol itself should not be leaking that a client is taking action. So people should be able to use it kind of in this blind capacity. Messages shouldn't be able to be linked to an individual. The actual conversations that are occurring should bleed no information, and ultimately it's impossible to tell who's communicating with who in this platform. From the protocol requirements, there's only 2 items here, but they're fairly large, right? The idea is that it can't rely on centralized infrastructure to maintain security properties, as well as operates in this highly unreliable transport mechanism such as peer-to-peer networks. And those 2 are enough to kind of weed out a lot of the other options. I have included a QR link here to the discussion on the VAC forum, where this is kind of spelt out in more details about the motivations for this, but to kind of give us a background for today's discussion. If we're building a new kind of protocol suite, we should learn from the ways in the past. And 2 things that I've learned kind of working in decentralized messaging for many years now is that cryptography isn't necessarily the hard part. It tends to be actually getting changes out to clients and getting it out into the network. It might take a week to implement a feature, but then it could take 6 months to actually have that being used by the network. A lot of that has to do with the code has to be out there. Clients can't read messages if they don't understand the payload that's coming in. And so the more that that's coupled to the software, the harder that is. And so I think it would behoove us to consider this problem of versioning and deployment from a protocol layer in order to help move faster. I think we've all seen protocol suites, particularly in the chat space, that have become ossified and stagnant because they can't get the protocol updates, or it takes too long to have those kind of pushed out. And so in the hopes of having a protocol stack that's fluid and adapts to concerns, we need to consider that from the get-go. As well as the secondary item is debugging unreliable delivery. Observability inside of a completely private protocol can seem like it's at odds to each other. But any sort of observability and kind of concreteness we can get from a client side allows them to determine whether or not they're missing messages or they're out of date. So less about gathering statistics on the entire network, but providing enough details for clients and developers to be able to debug and kind of have observability into what's happening on the underlying network. And so those are just 2 things that we'd like to kind of bring forward along with the kind of considerations. So if we kind of summarize it up, we need to have no metadata leakage around participants and conversations. It needs to work with peer-to-peer networks in order to have that censorship resistance. We'd want it to have an easy upgrade path to deploy new protocol features, and having this kind of observability into protocol failures would be very helpful for keeping it robust and keeping development moving fast. And so the question here is that how do we go about this? And so I'm going to introduce this concept of conversations as being the high level kind of organization of how we're going to approach this protocol suite. And in the simple case here, it's a framework for building and evolving a protocol suite. So what we're going to do is we're going to break down all of the operations into a pipeline. And that pipeline accepts content and outputs what we're going to call a protocol frame. That's just a payload that's generated by a protocol. So we're taking content, which is the text and the images and the videos from developers and people, coming up with a protocol and a way of just converting those into frames and then shipping them out. We're not going to worry about delivery, about how those are actually sent. So we're going to be agnostic to that, as well as the content that goes in. That should be anything. This is more of a transport pipeline than anything, rather than a fully described protocol set. And so being that agnostic on the conversation side means that we can define specifications about how to deal with content independently in a modular capacity. And so you're like, cool, this is just a simple pipeline. Hidden in here is this abstraction for managing change. In a typical pipeline, what we have is a layered arguments. So we have applications at the top, we have some protocol logic, and then we go through our reliability, encryption, segmentation, and then distribution. The problem with that approach is that the layers end up getting fuzzy as you add new context, and that adding a new encryption scheme means touching many places of the code, which then delays deployments, and then potentially has regressions and breaking changes. And so the idea here is that our conversations, instead of being horizontal layers, exist as vertical lanes. And we define them and give them a name, and each of those names is in fact a specification to define how that works. And so we should be able to deploy these new versions, or new versions of protocols, or even new protocols themselves alongside without breaking the existing case. And if we look at this kind of conversation mapping idea that I have down here, this diagram, you can imagine that a client exists with a map of conversation IDs to these conversation types. And each one is going to define everything it needs to know about it. It's going to define payloads, it's going to define operations, encryption techniques, and validation rules. All of that's going to be self-describing inside this type. And then they can exist kind of next to each other within a larger context. There's no need for this to be one, instead of versioning at the kind of client level, which then mandates that everyone has to update in this long kind of upgrade process. We version at the actual conversation level, which allows it to be more fluid and dynamic. Once again here, kind of pushing for that self-describing protocol, where we're not relying on the actual implementation details to define how messages should be parsed. We're defining it outright such that regardless of software version, you should be able to understand what's happening and how to process each message. And so, in talking about these vertical lanes, we go, well, what might some of these look like? And so I've kind of highlighted some in varying degrees of brightness. The ones we're going to focus on today are inbox and private v1. Inbox is an inbound only protocol for receiving invites and signaling messages, not made for content. And then private v1 is what we traditionally call like a chat conversation, at least a one-on-one. It's how users and developers push content from one side to the other. I've added some others just as a hint of what conversations could be. We're not going to talk about them today, so they're not too important, but you can see that group chats could fit in here as being different than one-on-one chats. They have a different encryption scheme, they have a different payload structure, but yet you could still just kind of plug it into the side, and clients could either support it or not. Even fainters, broadcasts, and potentially forums, those are lofty goals of potentially getting there and not important. But today's kind of conversation types we're focusing on are inbox and private v1. And so how does this work kind of as a high level flow? I've kind of provided a simplified view here. There's kind of three phases, right? There's contact discovery, which is this one phase. We then have initialization, which is this two, about how do we then get up and running with the information that we received from somewhere, and notify the recipient REA that we are looking to communicate. And then three is going to be protocol operation, about how do we send those messages back and forth. In this case, private v1 could be private v2, it could be group, it could be anything. But in case here, there's kind of three layers of discovery, initialization, and operation. And so in our case right now, in the simplistic one, we're going to consider contact discovery to just be out-of-band introductions. You have to use an existing channel to transmit the key bundle. That's an area that we're going to be looking at in the future, but for right now, we're just taking the simplistic approach. Inbox is going to be our invitation passing system, how we signal, how do we kind of send the prerequisites in order to get encrypted communication operating. And then we're going to use private v1 for that bidirectional double ratchet approach to messaging. Yeah. So if we start just kind of at the top on the contact discovery side, identity is a future piece of work. For now we are assuming that there is a 25519 key pair to identify a client. That's not a great approach, and I think we'll talk about it at the end here for future work. That's something we want to change. but that's future work, and right now we need to get moving. So we're just assuming a key pair for now. And it's assumed that you can send some message that transmits a static key and an ephemeral, or a static installation key and an ephemeral key. That is defined by a separate protocol. We're not really going to talk about it today, but you just need to communicate those two pieces of data at a band, whether that's over an existing channel you have or in person, doesn't matter. I am going to say that the channel does need to be trusted to a degree, not from security point of view largely, but from privacy. It helps to have that key identifier hidden. And we're gonna see this change significantly when we have an identity system, but it's more of a placeholder for now to kind of get us moving. The next piece in this pipeline, that initialization, is we're going to talk about inbox. And inbox is a deterministic entry point to reach clients. It's inbound only. It's used to coordinate and initialize conversations. And it requires kind of this recipient consent, right? Like the Rhea, our recipient, and Saro, our sender. Rhea needs to provide that ephemeral key, as they can only be used once. So there's a bit of control over who gets to access Rhea. And so it works for right now. You do need that static key and that ephemeral key in order to begin on inbox. If we dive into kind of how it's working underneath the hood, inbox is implemented using a noise handshake, and we're calling it XK0. It's really a KX for those who are familiar, but what we needed was to kind of reverse the sender roles in order to match our language. And so when you reverse them and you move this ephemeral key from a message to a pre-message, you get what I'm calling here a KX0. The 0 is because it is a 0 round trip version. You only have to send one message. And this is the static key from before, as well as the ephemeral key from Rhea gets sent here. And so if we kind of look at the privacy component, this is the payload that would be transmitted publicly. This is the top level unencrypted payload. We have an ephemeral key, which is going to be the sender's ephemeral key, which has no identifying information. So we're not worried from a privacy perspective there. This key reference is optional to a degree. It's possible that Rhea would have many ephemeral keys out there, and so there needs to be a reference to which one's being used for more of a optimization point of view rather than a pure protocol operation. And so in here, we're just using a 4-byte tag with a domain separator in order to identify that key. So there should be very little identifying information here. We do have this asterisk that the introduction should be sent confidentially. If that's the case, then there's no linkage. If someone was to see the internal contents and know that that ephemeral key belonged to a certain user, they could infer. It's a loose inference, but quite little identifying information, even in the worst case that is public information. We then have this static key, which according to noise is encrypted. So that's that static key here. It's encrypted with a Diffie-Hellman operation across the two ephemeral keys, as well as the sender's ephemeral key and the recipient's static key. So there's no identifying information there, and the payload has no identifying information. So on that first kind of contact coming in, what we get is a completely private, non-identifying encrypted platform, which also handles us with mutual authentication because we have the two static keys being involved. So if you trust the keys, you can be assured that this conversation is secure and from the people that you intended. And so that gives us great properties. Now, anyone who's following kind of decentralized or messaging in general might go, hey, why aren't we using the triple Diffie-Hellman ratchet or the extended triple Diffie-Hellman? And the truth is that in order to kind of leverage X3DH, it requires the storage of bundles to be efficient. As we currently don't have a place to store bundles or even an identity system that supports that, spamming out bundles on the network is very wasteful, as well as kind of breaks into our privacy model. Every message that's sent that has your identifying keys on it, shows that you were online to some degree. And if we don't need to be bleeding that information, we shouldn't be. And so in this case here, we're going with a little bit more of a stripped down, stricter approach of every session is initiated via an ephemeral key. So each one is unique, each one is protected. You can only use an ephemeral key once, which gives us great forward secrecy properties. And that's just how that's going to be until we look at identity. With our kind of conversations abstraction, it's easy to replace this if we wanted to. But for now, this is plenty strong enough, improved over X3DH, with very little overhead and management of key packages and safety from that perspective. So we've kind of gone this XK0 route using the Cha-Cha Poly and the Blake kind of package. And so yeah, once again, kind of reiterating that we get mutual authenticated encryption, forward secrecy, as well as zero private identifiers being leaked from kind of the inbox side of things. If we were to kind of go and look from the private V1 side of things, which if we kind of come back to our diagram is that protocol operation, right? This is how we actually want to communicate payloads from sender to receiver and back, because it is bidirectional. We're going to build a system here that has forward secrecy and post-compromise security to ensure that payloads are safe. We're also going to combine in segmentation, reliability, and encryption in one. When we talked about the kind of the conversations abstraction, we mentioned that you handle the whole vertical stack for a subsection of messages, right? And so to include that, we need to have all the layers that are needed in operation. So that's not just encryption, it's also this segmentation and reliability component. And it'd be fair to say that this looks like a non-standard approach. Segmentation is traditionally a transport level distinction. Why are we handling it kind of first here? And we can talk about that. So why does segmentation need to be before encryption, right? And the answer here is around metadata leakage. So if the data is public, you get this payload over here, this segmentation proto message. And so if this was just sent out on the wire, you would get a identifying message hash. You would also get a segment count, which would leak roughly the size of the payload, which would allow people to determine what content was actually being transmitted, depending upon segment size. That's more data we want to release or more data released than we'd like. And so the answer here is that we actually put the segmentation inside of the encryption layer. What we get is just confidentiality, integrity, and a lot of the security properties that we'd like. Since we have that encryption scheme, it seems like a good point to kind of put that inside. And then there's the question of, well, why are we doing it before reliability? Like, why is segmentation the first thing that occurs? And I have these two diagrams here. This orange square identifies where we have kind of reliability or an ID that we can call on. We're not going to get too deep into how SDS works. I'm sure it was probably presented already in this call series. But in this case here, if we did segmentation we did reliability after segmentation, segmentation after reliability, we would only apply the reliability to the content. And what happens is, should one of the segments be discarded or lost on the platform, the recipient would just know that it's missing, this A package. It wouldn't be able to kind of piece these together or have any content about what's going on. And so the only thing it could do is say, hey, please send that entire content again. And if that content is 100 megabytes, what we're looking at is just significant waste of bandwidth and throughput, as well as rate limiting concerns over resending pieces of payloads. On the other hand, if we do reliability after segmentation, that means that each segment is treated as a reliable entity and it has this kind of tag on it. The recipient could look at it and be like, well, I got A and I got B. The thing I'm missing is C, and then later reassemble without needing to rebroadcast A and B. once again, this is a bandwidth optimization point of view of we don't want to be broadcasting all of those components out. So in private v1, we segment first. We then make those segments reliable, and then we encrypt everything to ensure that it's private. And that encryption kind of mechanism that we're going to use is the double ratchet algorithm. These are relatively scary diagrams, but they're helpful just to kind of walk through and kind of talk about. The first thing we need to kind of make sure in the double ratchet is that it works for a peer-to-peer network in an unreliable delivery context, which we're going to talk about on the next slide. So keep an eye out for that. And double ratchet by definition provides forward secrecy and post-compromise security. And so, forward secrecy is to ensure that, messages into the, forward secrecy. Post-compromise security is the idea that if we have a compromise today, that it gets resolved into the future, that self-healing property. And forward secrecy is that if a message key was cracked today, you can't access the ones from the past. And so those two properties ensure that we have this kind of safe security system. It's highly desirable in chat where we have lots of messages flying back and forth. And so double ratchet's a very natural approach to kind of get both of those in one. We do have the parameters here for anyone who's interested, but we are doing this over the curve 25519 elliptic curve. We're using Blake for our hash function and Chachapoly for the encryption scheme, which is a modern fresh take. In this case here, we're not worried about interoping with existing clients, so we're free to kind of choose a more modern protocol suite or primitive stack, sorry, without any concerns there. And if you can upgrade to the newest, fastest and most reliable, then you ought to. One note here using double ratchet is that we are using the encrypted header extension. And the reason for that is, once again, to cut down on metadata leakage. So if we look at the payload here that would actually be published onto the network, this Diffie-Hellman here corresponds to the chain key that's being sent out, or sorry, yeah, the ratcheting chain key. And what's going to happen there is that would allow our data there, consistent, repeatable, reoccurring key there, shows that it's all part of the same chain. And while you might not be able to associate it to a individual conversation, it does kind of allow linkability of messages. Same with the message number and previous chain length. These are all required for double ratchet operation. However, they do have a header encrypted version. And so that means that through the same ratcheting process, we can derive a key that ensures that only the recipient can unencrypt them, or decrypt, sorry. And so that gives us great properties, right? So we're no longer bleeding linkability about which message chain that this belongs to. We're not telling how many messages are actually in the chain, because that's also encrypted, as well as the previous chain. So how many messages have occurred in the particular session are covered, and then the ciphertext is actually encrypted using the derivative of double ratchet, not necessarily the header encryption. And so combined together, kind of looking at it from that privacy point of view, once again, we have no leakage of information on per messages, at least at the encryption and payload data. As I kind of hinted at before, when we talk about data encoding and routing, that's another layer that we need to make sure that we have, private metadata protection. And that's something we'll look at in a future discussion. But at least from the encryption perspective, we don't have any concerns there. This is encrypted through and through. One of the things that I mentioned that we have to talk about before we can actually use double ratchet is to ensure that this, actually functions in a peer-to-peer case. And the peer-to-peer reliability mechanism that we're using is called SDS, or Secure Data Sync. Without getting into it, just because that's kind of out of topic for today, it's a separate protocol. But the way that SDS works is that it uses a causal history chain. And so when you get message 2, you have a link back to message 1, and then it tells you that if you received 1 and 2, then no messages are missing. You've got them all. If you missed 3 and 4, when you received 5, you would have a link back to the previous messages. You would notice that those are missing, and then you'd begin the process that SDS kind of governs about how to go and fetch those messages. And so this history chain requires that you can read the future or the last message in order to get access or know where to look for the previous messages. That is potentially in conflict with our concept of forward secrecy, where in order to read M6, you have to have the keys to M5, or at least the deriving keys, and that if you just have M6, you can't derive the keys for M5. And so there is this potential world that if we only have access to the end key, could we get stuck in kind of this cyclical dependency of, well, I don't know the previous messages that I need to get, but I need to get those in order to get the keys. And so the answer here is no, but I think it takes it's worth kind of showing, because this will pop up later for future research. The answer is or the thing that becomes important is, what is the factors that are going into these KDFs, right? There's some sort of information that goes in that allows the derivation process, and if this is known, then we should be fine. And so if we break up double ratchet into its 2 components, the symmetric ratchet and the Diffie-Hellman ratchet, on the symmetric ratchet, these inputs that I was talking about are all constants. And so in that case, it's possible for us, if we know the previous key, to actually drive this ratchet forward to derive future keys and kind of skip these ones in the middle. It's one of the defining characteristics of double ratchet, is this property to handle skipped and dropped messages, because it was made for out of order delivery. And so this works really great for us. Since we know all the inputs, we can actually derive this in and of itself for the symmetric key, which is used for successive messages from a single participant. And that works fine. The second case of the Diffie-Hellman ratchet is a little bit more complicated, because the state is dynamic. It determines on kind of this tick-tock of, Bob sends the public key over, Alice uses it to drive a new one, and then when Alice sends a message, it goes over, and then that ratchet kind of continues. So it does depend on data coming from an unknown source, per se. And so we need to make sure that that's going to work in our peer-to-peer case. And so in this case, we're actually fine for the concern about being offline and missing a few messages, because if we look at it from kind of Bob's perspective here, Alice is continually sending messages on the sending chain, and Alice doesn't ratchet until Bob sends a message out. And so if Bob was offline for a long period of time, i.e. no activity, Alice's encryption state stays steady. It does not move forward. It kind of requires participation from the absent party in order to advance. And that ends up being great for us to kind of handle this out of order case with SDS. And so from our perspective, there are no issues using double ratchet under this peer-to-peer model. This exercise is namely to point out that we will have issues with other encryption techniques, such as MLS and sender keys, because in those cases, the encryption state can ratchet or at least update without activity from all participants, which makes it possible that state update messages could be missed. And so that kind of just like raises a flag that moving into more group chat solutions, we're going to need to either revisit reliability or the how we manage kind of these state updates in some reliable manner. I know lots of teams are looking at state updates on a blockchain, which has its privacy implications, but at least gives consensus across the board. It appears at this point that SDS is not going to be a viable path to kind of dive into. without some modification or some changing of the parameters. Namely for that kind of, if we go back here, namely for this kind of loop here, right? Where if all you have is M6 and you need to be able to access the contents in order to read the previous ones, but you don't have the information because the inputs is dynamic and kind of contained in message 4, then you do end up in this cyclical dependency. Yeah, something to look out for as we move forward into kind of the group chat world is making sure that we manage those state updates in a very reliable way to ensure that no messages are lost and that people can read them. So if we kind of look at this kind of integration of inbox, private v1, and SDS, which are 3 different protocols that we're kind of mushing together here to create at least a one-to-one chat experience. We've shown that we're going to get 0 round-trip encryption across the board with forward secrecy and post-compromise security. Complete sender privacy, currently complete recipient privacy, at least from a payload perspective. We've shown that we've been able to hide that data sufficiently. Messages are not linkable to conversations, and content size, as well as other metadata, is also kind of protected. If we kind of look at the future work kind of aspects about things we haven't talked about or we need to dive into further, future work is identity is a big component there. What we want is a very robust, modern approach to identity where trust on first use has been inadequate in the past. I think it made sense when we were all dealing with phone numbers and sending SMS messages. Is the best we had and had some inherent security properties that were tolerable. In a more interconnected and Web 3-ish world where there are keys and you're less likely to meet people in person, having something more robust is important. From our perspective, it needs to support a bring your own identity. You need to be able to tap in and kind of build more integrated experiences if you'd like. That's not to say that's required, but at least have that option, as well as having safe revocation, which has been traditionally the hardest part about identity management in a decentralized capacity, is how do you make sure that revocations are visible? And so there are items there that we can lean on. There's existing kind of art to dive, or to investigate. And so it'll be a matter of kind of choosing the one that works best for us and kind of building that out. Future work there, which we'll come to see. The other item is ratcheting private identifiers is an area that we need to look at. There's this fundamental problem of kind of, what do we want to call it here? Performance, right? There's this question of, is this encrypted message for me? As all the payloads are moving through the network, one option is that individual clients can decrypt or attempt to decrypt every message. This is very slow, particularly when you're offline for a couple hours and you come back in, you have to process a series of messages. And if you're receiving messages from a fire hose, that could be a lot of processing power and or time to boot up. It also is ambiguous. Did it not decrypt because it wasn't for me? Or did it not decrypt due to a version mismatch or maybe even a protocol error? Kind of coming back to that observability, it'd be great to have visibility into what the actual state was. And so we can talk about deterministic parse trees in the future. But that's what happens if you try to decrypt every message. The other alternative is we could just put the recipient's identity on every payload. They would for sure know it's them. However, that's suboptimal from a privacy perspective. So finding a balance here would be helpful, or a new technique altogether. The idea of what we want to go look at here is deriving identifiers from the ratcheting process itself. That would allow them to be single use, known to the receiving participant. They would have a set of identifiers to be expecting messages from. Yet, because they're only used once, they would have very little privacy impacts, if any. So that's an area that we'd like to go look at further about how do you kind of add that performance upgrade to processing messages. Doesn't really impact the security principles themselves. It just doesn't play into the encryption side of things, but more into the routing side. But yeah, something we'd like to look at. Yeah, I'll just kind of summarize what we've kind of gone through here is that there's a in the specifications that we'll link to after this, you can kind of go read. There's this high level of conversations. They allow definitions of a top to bottom processing of messages to convert content into frames. Those can live alongside each other and be versioned independently. We've defined 2 so far: inbox, which is the noise-based inbound only message or message pathway for receiving invites and other signaling material that can be used by all conversations. We've also defined a one-to-one conversation type called private v1, which uses double ratchet and SDS in order to send messages over this peer-to-peer network, and have shown that those 2 are private, given the publicly available information. And so while there's lots more to talk about on the chat side, I might pause here for the day and ask if there are any questions.
Thank you for the presentation, Jess. It's really helpful to understanding the decentralized messaging. So if it is okay for you, I'd like to ask a very, basic questions, very generic questions. Some messaging applications say themselves are decentralized because they just use the self-storage. So is it enough to make it any chat application is decentralized with this feature? I guess no, but I just wonder your idea. What can be the definition of the decentralized messaging application according to you?
Yeah, so I think that's an excellent question about a misoverused term, right? A lot of people claim that they're decentralized because they don't run on AWS. I think when we start talking about decentralization, from our perspective, it has a lot to do with censorship resistance, right? And so the question is if a key piece of infrastructure was made unavailable, does it still work? And so that decentralized kind of implies that there's a robustness to availability attacks. And so I would define the litmus test would be can N nodes go offline and it still work? If you rely on a certain individual node to be offline, particularly if we're talking about key packages are stored centrally in a single place that doesn't move, that becomes problematic. I often hear the case of more federated approaches being referred to as decentralized because you can just run your own. I think that definition kind of jars me a little bit in the sense that you're still running at a known address and a known location that could be, kind of taken advantage of or brought offline. And so, I consider kind of federated approaches to be multi-centralized. There's lots of different locations, but they're still running in a single spot. And so we're looking for non-single point of failure, robustness under different network threat actors, and this ability for it to kind of morph and heal from a network connectivity point of view.
Yeah.
Did I answer your question?
I think yes. The censorship and censorship and robustness. I think the key. And yeah. Is there any question from here? Yes, Alexander.
Yeah, hi. So thank you for the presentation. It's very interesting, and I would like just to ask about I mean, in the list of requirements, you listed sender anonymity.
Yeah.
Right. And I mean, part of this, like achieving this, is of course it's encryption, right? But then also, like, how do we ensure that in this protocol kind of like a traffic analysis, like a statistical analysis of traffic on a network is prevented. Because I mean, if, for example, we can have like very good encryption, but then, I mean, actual timing of messages, like and when they released and then when they received and so on, they can reveal, who is communicating with who. So yeah, this is my question.
Yeah. So one, it's a great question, right? And I think I kind of skimmed over it due to, maybe clever boundaries in these protocol specifications, right? From a chat point of view, we have to be kind of agnostic to some things in order to move forward. And so we've kind of drawn the line and say the platform and delivery service that you'd like to use is up to developers to choose, right? We might provide guidelines for that. And so that's how kind of, from a chat protocol point of view, we can be like, hey, choose one that has those properties. Not necessarily passing the buck, there are options, right? So decentralized peer-to-peer networks help with that because it's not always clear about how messages got into the network. So there's not necessarily that chain that says, hey, it got into an entry point there. And so if everyone is fully connected in a mesh, it's hard to tell whether the message occurred from you individually or not. Mix protocol adds in some help here by being an improvement upon Tor about making sure that we have consistent routing through peers without necessarily knowing who the originator is. So in that peer-to-peer side, there are realms. I will say that I kind of am hoping or relying on others to kind of build out that network in order to make that functional. But there are techniques to do through Mix and advanced peer-to-peer networks. As soon as we have a centralized component or a server that you have to go through, gathering that data becomes significantly easier. So that's why we need to be careful about avoiding centralized pieces of infrastructure. But peer-to-peer networks, Mix protocol, helps us move that buck forward, and a lot of the research from Vec and the rest of the Logos team is going to move that forward.
Yeah, thank you. I mean, this is sort of like a partially answers the question, because like for me, it's difficult to imagine how one can sort of claim sender anonymity without some sort of mixing of messages.
Yeah, that's fair enough. I mean, I think we're drawing the line at the border of we're not contributing to worse sender anonymity. At some point, it's going to be a you have to look at the entire protocol stack and make sure. If you decide to run this protocol centralized, which is entirely possible, you're right that you would have poor sender anonymity due to traffic analysis. I think it largely comes from, is there any cryptographic links to messages? I would go forward and kind of, if we want to add some ambiguity, there's no need for messages to actually originate from the client that's put forward. They could be passed over a separate mechanism. So there are ways to kind of add that in there. But yeah, you're absolutely right that this kind of skims over the complexities of networks and privacy from that component. I think that leaning into the composable nature and allowing others to kind of work on that without necessarily hamstringing them is the important part here. And that's where the work's kind of focused.
Mm-hmm. Thank you.
Yeah, great question though. I mean, I think it's very important that we do kind of focus on the holistic side, and just because we're solving problems at one layer doesn't necessarily mean that the solutions are there. I would say that people are working on this, specifically the Waku and the Mix side of things, about how to add that through. And I might point you kind of in their direction to follow the research and gains there.
Any questions? Yes, SB.
Hello. I would like to ask about the conversation being like a vertical stack. You talked about the advantages. What would be the disadvantages, I guess, of doing it this way instead of a more, I guess, yeah.
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 No, great question, right? Because there's no free lunch when we start talking about design elements. I think if we go back to just kind of the high level one more time here, when we solve problems, we're kind of turning dials in order to get the features that we want. And we're often talking about performance and how we get that, and security. But there's another one here called complexity. And I think that complexity is probably the one element that we can use in order to get our privacy goals and our reliability goals and our flexibility. So in this case, what we're doing is we're adding complexity through the system, and namely it relies on a well thought out API layer for what conversations are. And I thought I had a slide on it, but apparently I deleted it last night. I apologize. If the abstraction into the abstraction layer and the top level API into conversations doesn't fit all the use cases, then it breaks down. And so the downside here is that it takes some effort to make sure that we do have a robust abstraction layer there. It's also hard because right now it's pretty nascent and it needs to be improved. And we will only learn through process about how to dial that in. So right now it includes sending of a message. You pass it content and it spits one out, as well as handling payloads. Those are the two major functions about the interface into a conversations. And so, yeah, I think that there's extra complexity about how do we handle runtime polymorphism and kind of dealing with this, different payloads that might be on the implementation side, is really the downside of using the conversations versus something that's a lot cleaner. My argument in favor of it would be, implementation complexity is probably the one thing that we can kind of control. It's suboptimal, but if that means getting other benefits in terms of deployability, moving fast, then I think that makes sense. Yeah, good engineering takes time is the adage that I would kind of kick towards. So to answer your question, complexity on implementation on the high level is what is being at cost here, versus if we just had it fully integrated, it'd be pretty straightforward.
All right, thank you.
Great question.
Any more question? Maybe I have a small one. Is there any mechanism for recovering sessions, especially with different devices? I guess the inbox will be the point here, but also maybe this can be addressed in the application level, right?
Yeah. So that kind of goes back to identity, right? So this concept of having, a user, and users have, clients and installations. The abstraction that we've taken for now until we do the identity work, which will bring on kind of those robust systems, is that what we're talking here is about installation keys. And so an installation is inherently one, application instance. And so in that case, that's not something that's supported at this moment. The protocol itself the protocol suite itself is agnostic to how that happens. It's not really required. If we go back to, here, it's a matter of replacing this introduction system. As long as we can get, this S and this E through, we don't necessarily have it figured out yet, but the goal is that we kind of avoid the trappings of previous double ratchet implementations that use, an identity key, and then that has to be synchronized across all the client's installations, and rather treats installations as separate entities on their own. That gives us a much more flexible approach, as long as we can kind of handle group administration easily. So yeah, TLDR that's that work chunk that I was talking about in the future about identity. And having that kind of support. So there should be a line item here for must support multiple devices.
Yeah, thank you.
Yeah.
Any questions?
While people are thinking there, I might just jump in and kind of reiterate here on the identity side of things. I think that's one of the areas that I'm excited to dive in and kind of get working on. Unfortunately, there's a prerequisite of things before, right? I can't just jump into identity when we don't necessarily have a chat system going. The key priority is to kind of get the protocol suite out in front of developers so that they can start testing and making sure that no particularly API changes are needed. You know, when SP asked what's the downside, we want to be testing that kind of conversation interface as quickly as possible, which means that identity kind of needs to get bumped just due to, you know, scheduling. But I do think that the identity is going to be the kind of the major component to this chat protocol suite, because what we're really talking here is about authenticated communication, right? How do you have confidence in who you're talking to, and how we handle identity in a safe, consensual and private or privacy preserving manner is going to be key. And so we have lots of thoughts and ideas. Yeah, waiting for that to come to the top of the to-do list.
Yeah. And also the necessity of the STS here, because the double ratchet requires ensuring the states, right? So the sender and receiver needs to be needs to have the consensus about the sending and receiving. If there is some packets are dropped and with the unreliable channel, the receiver cannot apply the receiver receiving ratchet. So STS is really necessary here, especially for the P2P systems. But do you think that the STS creates some burden to like a throughput, and it has some effect on the user experience, do you think?
Yeah, so I mean, if you were to ask me, would I like STS to exist? And the answer is no, right? In a perfect world, we have a decentralized, censorship-resistant, you know, highly private network that also has perfect order and all the payloads are visible. That's not what we have today or what we've been able to find. And so STS is to try to bring reliability, which is a requirement for a lot of these protocols. Or, you know, the entire double ratchet chain kind of implies that these messages will arrive, at least, and even more so as we start talking about group like MOS. So I will say that STS is kind of our best foot forward for managing that reliability in an unreliable world. Its impacts on users hopefully should be light. You know, I think the real impacts are things we're gonna have to measure is on rate limiting. How do we make sure that the messages being sent are contained? And that's why you can see that we're conscious about the ordering of messages. Yeah, here about you know, we do want to minimize those payloads going across. I think overall, if you look at the actual payload structure and everything else, in terms of latency, I think we're looking pretty good. I don't see too many concerns there. You know, I think it's just going to be how to, like anything, how do you keep reliability functioning while also keeping a rate limit on the network in order to kind of control excessive messaging from bad actors. You know, that will always be a balancing act until we look at, you know, potential other well-structured, well-ordered, highly available and reliable channels for sending messages. But that's, you know, future work to kind of balance out.
Yeah, of course. Thank you. Thank you. Yes. Any more questions? Last call. Looks like no. So let me thank you, Jazz, for exciting work. I'm really personally looking forward to use the decentralized messaging in this centralized world mostly. So, and also thank you for the audience. And if you want to jump into the discussion on forum.oac.dev, you can just visit the forum, or you can just scan the QR that Jess already presented. And for the next episode, we have no fixed speaker right now, but hopefully see you next time. Yes, you are open. So thank you.